And we can't hear you. You're muted. There you go.
Is that better?
Now it is much better.
Ah, excellent. The computer that I have video on is different from one I usually use. So new keyboard, always a problem.
Yeah, just another couple of minutes to go.
Yeah. Sorry, I was able to do this when you first requested it.
No, not a problem. I have thankfully had very good guests at every planned episode, so
Good.
no issue at
It's a
all.
chance to talk about things. There's nobody around here I can talk to about stuff like this.
Oh, wait, if you want to come more than once, you're more than welcome to. I don't think we've actually ever met since I became conscious of my surroundings, at least.
No, I don't think we have.
I mean, we probably met when I was very little. I don't remember.
Probably APL 76, maybe.
No, I wasn't born yet, but
Oh,
I only started
would
attending
be
at,
a big no then.
yeah, I started in 86.
86.
86, and I was probably mostly there until 90 or something like that. And, might have skipped, I'm not sure. Skipped, no, 89? Not sure. But I don't remember
Lost
any of
were in
this.
these different groups.
Yeah. I don't, frankly, I really don't remember any of these conferences at all. I just know I was there. Yeah, so. But I mean, I grew up hearing about you.
How many of these have you had?
Let me see. Memory isn't what it used to be.
Tell me about it. Yeah.
Yeah, we've had 6 episodes. So the first one was very informal. So it was just some people getting together talking in general, and then we liked it, just 3 of us, and we liked it so much we decided to make it like a regular monthly event. Then it became this, you know, inviting
Huh.
the big shots and having them either present or asking them questions, and so it just kind of grew organically. So you can see the recordings of the previous 5 episodes, and then
Yeah, you sent me the link for those. I didn't take the time to do it.
that's fine. Then you'll be original.
Yeah. I consider myself pretty lucky that I'm still busy at this age.
Yeah, I mean, as macabre as it may sound, I wanted to catch people on video before it's too late. Right? There are
Yeah.
big APLers that are not with us anymore. So,
Yeah, just recently we lost one.
yes, Roger. Yeah.
That was distressing. Roger Huey and I and another APL colleague who have been going through cancer have been in a email group since early 2019. So
Oh, really?
we're sort of in touch. But I only found out about his passing from a note from somebody in the UK.
Yeah. So yeah, it is time in every time zone, and with us today, as you can see, is Jim Brown. Just briefly, for those that don't know who Jim Brown is, uh, everybody knows the name Iverson. And Iverson obviously laid the groundwork for it, what brings us together today. But I think if there's one person that had an influence on what APL looks like today, then it's Dr. Brown himself. Yeah. And I mean, I'm sure you'll be speaking about this as well. But there was in the days of extending APL to have more than just plain arrays of characters and numbers, characters or numbers, I should say. There were doubts about how to extend the language, and
Indeed.
the design you came up with was the one that proved itself to last. That's what every APL in existence today does. So that I don't think there's any bigger influence on modern APL than yours. So go ahead, go for it.
Well, what do you want to talk about? The early days?
To talk about, well, you can talk about whatever you want. It's very informal. The early days is what I would love to hear about. And if
Okay.
you run out of that, I have collected some questions from various people that have asked that couldn't make it today, I think, and but they wanted me to ask you some things. But I would I would love to be like put into that room where things were happening. There was fighting going on, there was discussions going on, and what were the consideration? How were the personalities? How did you make the decisions and so on?
Okay. Well, I first came to know the name Ken Iverson not long after I joined IBM Federal Systems in 1965. About a year later, a colleague came up and says, Guy Iverson and some other people, they've reduced the System 360 to a single symbol. He held up a copy of the System Journal with the formal description of the System 360. Of course, that wasn't exactly true, but it piqued my interest because it's the kind of thing I was interested in anyway. And so I ended up picking up Iverson and Brooks' book on automatic data processing, and then finally a programming language. And so I was interested in that sort of thing, but that was it. And then quite by accident, must have been, I don't know, 67 or 68, the local Association for Computing Machinery chapter had a dinner meeting, and a colleague of mine and I thought we'll take our wives out to dinner. You know, if you want to impress a woman, take them to a computer meeting. I've always said it doesn't seem to work that often, but still, that's what we tried. And didn't even know who the speaker was. It turned out to be Aidan Falcoff with his portable 2741 that came in 2 suitcases, so it was just barely portable. And he gave this just magical talk, communicating with the telephone operator, telling them, please don't disconnect us because you're going to hear funny noises. But, you know, and one of the first things he typed in was 2 space 3, backspace 5, 2 space 3, backspace plus, hit return, and he got 5. And he was showing visual fidelity. My colleague and I were just blown away by this. You know, that was such an amazing concept. Our wives were somewhat less impressed because they had figured out the answer without all this technology. And I don't think they understood ever why we were so excited about that. So one of the things that really impressed me in that meeting is that Aidan gave recognition to some of the people who had worked, in particular, Larry Breed and Dick Lathwell. And I'd been to IBM meetings before, and I've been to many since, and you never gave people credit for things. You know, it just wasn't done at IBM, and here was this guy, he did it. So that was my first encounter with the name Larry Breed. And went back to my office in IBM Federal Systems, and we had a terminal that you could dial into Yorktown. So I gave it a try. did right print message, no, right print OPR to get the operator. She set me up with an account, Jerry Barrett, well known to the IBMers. She was the first APL operator, we like to say. And yet did apply herself to functions to produce other functions. So she was a strange operator in some sense. And so I started playing with APL with this account that she set up. And actually, I don't think it was called APL yet. I'm not sure when the name came. Anyway, she sent me a message saying, give me your account information so we can charge you. So I quickly signed off and went to my manager and tried to get an account and said, you know, we don't have time to play around with stuff like that. So after some months, Syracuse University was sending teachers from Syracuse down to the Endicott labs, and we could attend graduate school classes 1 day a week. And when doing that, I learned that Syracuse University was going to get an APL system on site. And so I ended up leaving IBM and going on campus to run their APL system. As luck would have it, after 2 semesters, I ran out of money and had to get a job. So I wrote to research, IBM Research in Yorktown, and asked for a summer job. And I wrote to Aidan Falcoff and asked for a summer job. And IBM Research said no, and Aidan Falcoff invited me for an interview. And so I ended up getting a job that summer. And the first task was to extend base value and representation, now called encode and decode, to work on higher rank arrays. And there was a lot of interesting things about that group at that time. I found out at the end of the summer that Larry Breed was my manager. I had just assumed it was Aidan. Nobody ever talked about things like that. Nobody cared about things like that. The only thing people cared about was this notation that we were developing. And you're right, some of the arguments were very intense arguments. And typically, Aidan Falcoff take a very negative approach to things. And Iverson would take a very positive approach to things. And we'd argue things out. And by the time that they reached agreement, we were all pretty convinced that they had made the right decision. And I can't honestly think of many cases, if any, where they didn't do the right thing. But it's surprising me how difficult it was to come to those decisions. And the practice then was consensus. We didn't do something unless everybody agreed that it was the right thing to do. And as the notation matured and the group became bigger, that finally became impractical. You reached the point where you couldn't get everyone to agree. So I found out that Larry was my manager at the end of the summer when he gave me the exit interview. That was the first I knew that he was my manager. And he messed up the paperwork and I wasn't terminated. So I just kept working from Syracuse on a terminal, which was kind of unheard of in those days. This first job I had to do, representation and base value, encode, decode, was interesting because the extension would mean that existing cases worked differently, because you could do the 222 representation of 5 and get 101. But if you did the 222 representation of the 1-element vector 5, you used to get 101, but now you'd get a column vector 101. So the shape would change, and Larry was concerned that that could affect people in their programs. So he had me put in a counter in the code to count how many times we did representation of a scalar and how many times we did representation of a 1-element vector. And we expected 1-element vectors because the shape of a vector is a 1-element vector. So that was expected. We couldn't believe that there were just overwhelmingly more representations of 1-element vectors, orders of magnitude more. which put doing the work on the extension at risk. Well, I discovered that there was another summer employee. His name was Seth Breitbart, very intelligent guy who did great things later on, who overheard us talking about putting this counter in the code. And so he put a terminal into a loop taking representations of one element vectors. And that's why the count was so high. So when I saw this was going on, I put 2 terminals in a loop doing representations of scalars. Eventually my counter overwhelmed his and I was allowed to do the work. So that was my first job at IBM.
So then maybe I can ask about that then. There's something that's a bit odd in in how represent works. A couple of things that I always found odd. One is the order of the axis. It's very often you'll find that the result is immediately transposed.
Yes, yeah, that's true.
So was that something you worked with, or was it always like that?
No, it was something that we definitely had discussions about. And as I recall, the reason that it ended up the way it was because of an equation involving an inner product that did the inverse. And it's the way that worked out cleanly. I wish in retrospect we had kept track of what led us to make decisions, especially the bad decisions. Everybody remembers what the bad decisions are, but nobody remembers why we did it. Because of course, in hindsight, it all looks obvious that it should have been different. I know one of the papers I wrote was what's wrong with APL2. Delightfully short paper, I thought. So I don't think too many things wrong.
You mentioned breaking the equivalence between a one element right argument and a scalar right argument. But that's another thing that's strange. The left argument doesn't distinguish to today. So if you use a single number on the left, say you convert to binary, it treats it as if it's a one element vector.
That is true. And that's kind of through the whole notation, the way that one element things are treated. And a lot of effort has gone into trying to formalize how that works. I don't think always successfully.
No.
But,
yeah, I always thought that the obvious
where implementations tend to differ is because we handle some of these, a 1x1x1 array against a scalar or something.
Exactly, yeah. Yeah, that's something I've always found was the obvious choice. Having a scalar on the left side of represent or encode should extend to as many digits as necessary. So you don't have to do logarithms to figure out how wide you need it and so on.
Yeah, but then you get variable length results, and those are very hard to handle in an array notation.
That's true.
It's one of the reasons why we went to nested arrays, as they're defined now, as opposed to ragged arrays. We definitely considered having arrays where rows had different number of columns, for example. And that could be done, or having columns that had different number of rows so that the shape of the array wasn't square. But we went instead in favor of having strictly rectangular arrays, which contained strictly rectangular arrays. But I think was a good way to do it. It kept things pretty simple. So after about 3 months of working from Syracuse, then I joined IBM in the Philadelphia Scientific Center, and that's where the first lines of APL2 code were written. Alternate interpreter that would run under the APL SV supervisor. And we basically, most of the development of APL2 was done by trying things, getting comments from people, adjusting things, Um, that effort was eventually moved to IBM in Palo Alto. That would have been around 74, I guess. I think it was 71 when I graduated and joined Philadelphia, and it was like 74 when they shut down the scientific centers and we moved to the Palo Alto Research Center. And shortly after there, Larry Breed came back again. He left STSC, where he had been for some years, and rejoined IBM, and now I was his manager.
So work on APL2
It didn't
or
matter. Say,
the work on APL2 or what became APL2 eventually started that early in the early 70s?
yes. Basically, IBM gave me 10 years to produce this offering, and the first experimental version was released in 1982, and it had been 10 years in the making. It was not 10 years solid effort. There were 10 years of stolen moments working on it, because we were supporting, APL SV and still in those days APL 360. And also because there were a lot of differences of opinion about how things should go. In particular, the argument over the enclose of a scalar went on forever and never was really resolved. I think it was in 2010 I gave the APL meeting in Berlin, where I gave our reasoning for treating the enclose of a scalar the way we do. And to my knowledge, that's the first time we talked about that argument outside of IBM. And I found it, compelling, but not everybody did. And for many years, probably at least 5 years, we had both things implemented in our test system. And we had a system variable, quad AX, for axiom system, where you could choose axiom system 0 and get one result, and axiom system 1 and get another one. Maybe it's like a precursor to migration level.
Yeah.
The quad ML in the dialogue APL. But at some point you have to make a decision, and that responsibility landed on me, and it was a really tough time, because I had respect for the people who differed in opinion on how it ought to go. Aidan and I certainly had serious differences for many years. And yet when I worked for him, he always took care of me. I never much worried about my career, but he took care of it. So that was good. One of the things I remember, I keep coming back to Larry Breed because I was quite moved by his passing recently in the memorial meeting that I attended with him. When he first came to Palo Alto, I noticed that whenever he had to write some sort of test program, he'd call the program foo, F-O-O. I asked him about it. He says it comes from foo for all. Word you can look up if you want. And to this day, IBM implementations, if we have storage, which is not initialized, we set it to F00, F00, which is foo, because of Larry. So we could recognize, okay, that's our storage and we didn't initialize it. We could recognize it. So sort of as just to play a trick on Larry, I changed the scanner in APL so that the name foo was not acceptable as a name of a function, or any string of characters which contained FOO, and watched him try to write his little sample programs. It was great fun. He just understand what was going on.
So today in programming world, or maybe I'm mistaken, I thought everybody used foo. It's only the APLers that use foo.
Nowadays, you see it all the time. You got to come up with some kind of name, and it's.
But this is where it all started.
Yeah. The mistake I made was we had a release of the experimental APL2 product, and I forgot to take that code out. And so we shipped it to customers. And we never heard from them. So maybe the customers don't use foo. I don't know. I didn't want to ask, because it would be a defect in the product. You don't want defects in the product. We had another release as soon as we could, and without that code in there.
Oh,
So
so
that's my background on AP. What do you want to?
well, that I mean that invention. This is where foo happened the first time, and then that
To my
spread.
knowledge.
It spread all over the world. The whole world knows foo then because of what it started with. Amazing. So you created APL2, but in APL at IBM, did you also use APL2 for internal projects?
Yes, all the time. There was always a resistance to it, though, because it was so different from everything else. But for example, there was a query management product called QF, Query Management Facility, which was written in APL2. Had all this wonderful function, but when it came time to get it ready to give out to the world, they wanted to rewrite it in a real programming language. I don't recall exactly how they phrased it. And of course, they had to take out a lot of the function to do that. So QMF ended up having much less capability than the version that was written in APL2 had.
So but it was an early example of using APL as a prototyping language then.
Yes. We certainly did it. All of our work, all of the primitives were all modeled in APL long before they were ever actually turned into primitives with code behind them. I still have the tapes from the 5100, the first portable computer, supposedly 50. I think the IBM PC was a 5104 or something like that. Very similar. If you look at the APL Dinosaurs Facebook group, they have information about that. And I did a lot of the extensions to APL using APL on the 5100 because I could carry it back and forth. And at some point, I left IBM on the West Coast and went back to Yorktown to try to finish the APL work. And I don't have the years exactly in my head, but it's sort of when I look back at it, they say if you want to be good at something, you should work with someone who's better at it than you are. And I really had. First, that was incredibly easy for me to do, but gee, those people happened to be Ken Iverson, Aidan Falkoff, and Gene McDonnell, and Trenchard Moore, and it was wow, what a lucky circumstance that was for me to get to work with those people, and people outside of IBM as well. Bob Smith was extremely influential in my time at IBM. I remember the meeting when he came to IBM Santa Teresa to tell me what he thought was wrong with our experimental system we put out. And he was right, and I changed it with great consternation from Aidan Falkoff.
Remember what it was?
Yes. It was really kind of the fundamentals. It was a question of, for the example I usually give is outer product. What happens if you do outer product catenate, for example? And I don't want to go into all the details, but with the definition we ended up with, if you do outer product catenate on a set of 4 vectors, you get the Cartesian product of those four vectors. Each has items inside the array. They wanted a flat result so that if you did an outer product, you got a result whose shape was the shape of the left argument, catenated with the shape of the right argument, catenated with the shape of the items. And they better all be the same length.
Or you would have to pad. So
Without a comma, you'd get a left by right by 2 array. But if you did out a comma on 3 arrays, then you'd end up with left argument, catenated shape of right argument, catenated 2, which can relate to anything that anybody ever wanted to compute. And the argument was, well, just do outer product, catenate, and you get the result that I wanted. So that seemed like a good compromise. I'd have to use some each, but I'd get what I want and they could have what they want. That was a mistake to try to do that. And so between the time IBM came out with the experimental version in 1982 and the real product in 1984, that was changed.
So if I understand right, you're saying it's the original result would be the equivalent of doing a mix of today's outer products, right?
Yeah.
Right. I can see why some.
Yeah, I like, you have to try to compromise. You can't have everything your way. So you try to compromise. Now, I think maybe that's a mistake when it comes to formal systems. I mean, formal systems should be run by equations, not opinions. And so we tried to come up with the equations that described what we wanted. And so, the shape of outer product was one of those that we decided we would maintain in the nested array world with what it was in the pre-nested array world. But still, those are choices. The formalism doesn't tell you exactly what to do. It tells you what things will match that formalism. You still have a decision to make. Which alternative are you going to choose?
Oh, one thing changed though. Bracket indexing into a literal vector changed between APL 360 and APL 2, right?
Yes, it did. And to this day, I think that's still a discussion. Roger and I discussed that at great length over the last couple of years. And I don't want to get into too much technical detail, but when you have constant arrays, a constant vector with an operator, the operator appears to strip off the rightmost element of the vector if it's the left operand. And the argument is they talk about why it's bad to split numeric constants. But my position is APL doesn't have numeric constants. And the original APL, when I first went to Yorktown, didn't have numeric constants. And Larry, if you wanted to write a vector, you wrote left paren 2, 3, 4, right paren. Looked just like it does in mathematics books. And Larry was very proud of the code he had in the scanner that would go through and recognize that and store it in the system as 2, 3, 4. So that the interpreter didn't have to do all that extra overhead figuring it out.
So this was an early prototypes of APL before APL 360 was released, that you needed to write parentheses and commas?
That's right. Looks like a math book.
So yeah, so who came up with well, it was important to recognize this, otherwise it would be very expensive to evaluate.
Oh yeah. Great amount of interpreter overhead if you have to scan those individual tokens. And that's why Larry was so proud of his code. And I know that Larry was in favor of the numeric constants. Aidan was not in favor of it. And his argument was, and is still reasonable today, I think, if you say 2 space 3 space 4 plus 5 plus 6 plus 7, it looks like you're saying 4 plus 5.
Yes.
That's what it looks like.
I teach a lot of people APL, and I pretty much hit this one every time. I tend to add a lot of spaces around the plus to try to make it more clear.
Yeah, that's right.
And I see people putting parentheses around the vectors for the same reason. So who came up with this for ideas first to allow spaces and no, or it's not just spaces?
It was Larry. Pretty sure it was Larry. And Dick Lathwell, as I recall, also supported that. I don't remember what Ken's position was, but I remember Ken was opposed to it. And basically, without actually ever writing down that rule, but when we did APL2, we did write down the rule that arrays are more important than functions. And so you build arrays first, and then you apply functions. And that's why the 2, 3, 4 plus 5, 6, 7 works the way it does, because the form 2, 3, 4 is more important than plus.
Right, but then with the indexing, you end up in trouble with the operators. The way APL2 does the operators, it strips off. So they're saying operators are more important than arrays.
Yeah, the way we look at it is we don't have numeric constants.
Right.
We have arrays, functions, variables, operators. And if I have a bunch of things written down, A, B, C, D, E, F, G, then you got to say, what are each of those things? Well, A is 2 and B is 3 and C is 4 and D is plus and things like that. That should be the same if I write 2, 3, 4 with constants, or A, B, C, where A, B, and C have those as values. So we don't split numeric constants, we form them at scan time. Now, because we do store a numeric vector as a single token, in fact, the implementation does strip off an item, but we consider that an implementation consideration, not a language consideration. So we don't make a distinction between an array and a constant if the array has that constant as its value. And I go into great detail about how you use parentheses to, first you parenthesize everything, and even single numbers, you put parentheses around them. And then you write the rules for which parentheses are redundant.
Right.
And that's what gives you the hierarchy of execution.
You don't have to be afraid of the technical content here. Apparently the audience loves it. So
well, that's a good point. That's a good point. I'm not talking to people that even care about these things, let alone would want to discuss them.
No, it's very welcome here. Right. I know that dialogue did not have the courage to break backwards compatibility. So in dialogue APL, operators cannot strip an element of a literal numeric vector or anything else. The stranding is stronger than anything. And so you can index in, you can say 1, 2, 3 bracket something, and it will also work because it behaves like APL 316.
So it's not indexing, it's indexing this
Yeah.
constant. But if you said A, B, C in parentheses, then it would apply to the whole thing. If you say 1, 2, 3, 4 in parentheses with brackets, what does the bracket apply to?
Well, you have to, if you want to index into the last element, which would never really make sense, but then you'd have to parenthesize that element with the brackets. So
yeah.
I don't know, how often do you index into a literal like that? I don't know.
Almost never.
Yeah.
Pretty much. And so these things they take a lot of the time of the implementers. in a practical sense, doesn't make a lot of difference. Although one of the good things that APL did was to make limiting cases work correctly. You know, you don't have a problem if you do the plus reduction of an empty vector. You know, it does the right thing because it defaults in the empty cases to what you would expect. There was a lot of arguments about what those results against empty arrays should be. And
So how about each then? That's something that often bothers me. If I write a function that say has side effects and apply it with an each over an empty array, then the function gets called once in order to establish a correct prototype result. But that can have disastrous effects, writing a file name that's all blanks and things like that. So was there a discussion about that?
oh, endless discussions about that. And we basically ended up realizing that there really is no 100% correct way to do that. But if empty arrays are going to have type, you have to do something to determine what the type of a result should be. And we actually at one point came up with a scheme where you could programmatically say what the result of empty applications would be. If you write a defined function, we had a facility called System Labels, which we never actually released. And one of the labels would be empty. If you're going to apply an empty case, if you're going to be applying function to prototypes, you could say what you wanted it to do.
NARS has this today, or NARS 2000 at least has this.
NARS 2000 has a lot of interesting things in it. One of the things I like best about NARS 2000 is ball arithmetic.
Yeah.
You look at it, I mean, my gosh, you can apply a function, a whole bunch of functions, and you know within what error it might be. And people tend to accept the results they get out of the computer as being correct. And they're not. They're almost always, at least mathematically, incorrect. You just hope they're close enough to matter. A situation at IBM where we had a APL program, I don't remember exactly what it did, but it was used during the planning phases for figuring out what you do next. And they also had a version of the program written in PL1. And these two programs often produce different results. Now, you're going to do planning. What are you going to do? Which one do you believe? Their solution was to stop running the APL model. Now they only had one result and they could believe it. And apparently it kind of didn't matter what that result was as long as it was unique. It's very
Didn't matter if it was right or not.
do that kind of thing. You know, companies run programs and say, oh, this is a result on what I computed before. We'll just stop running that one.
Oh. So what was your favorite usage or application of APL2 at IBM?
Wow, that's a tough one. Favorite application of APL2. I mean, we just used it for everything. We even have a IBM stock application written in APL that we still use today. That you know, it's hard to keep track of stock in companies when they have splits and fractional shares and all this stuff. And when you want to sell stock, you got to figure out what's the cost basis for it. And we have an APL program that does that. Still use it today, written many decades ago. Now, I don't think I can answer what would be my favorite, because I use it for pretty much everything. You know, I'm working on a couple of projects now that involve APL and that involve arrays. And almost always model them in APL2 first, or dialog APL, depending.
So then I have to ask you about the switching over of monetic up arrow and monetic right shoe.
That was very distressing for me to see that by default dialog APL as what we had in the experimental APL version, not in what we ended up with in the program product. I still think up arrow as first. And I have trouble writing programs in dialog APL sometimes because of that. And I really don't want to use migration levels. You know, that would get around the problem. If I was, well, I don't know, doing a real application for somebody, maybe I'd make use of migration level, but I'd rather use the language that they believe is the definition of the notation. You know, I want to use that. And that's a really hard one for me. I remember being sort of shocked when I saw that. I was with John Scholes and the name escapes me. I know he's not with Dialog anymore. He took over as sort of the chief technical guy for a while. The name escapes me, but
Jay Fode, I guess.
yes, Jay. And we were doing something on the terminal, and he did a left shoe, and I looked at it sort of funny. He said, "Oh, here, I'll set the migration level, and we can use up arrow." I was shocked.
Sure, but who changed it? You changed it? Because the dialogue was just
changed
rushed
from our experimental system to our program product system, making a difference between disclose and first. And that was largely at the doing of Alex Morrow, who was one of the early developers of APL and became the APL manager. And I'm still happy with that decision. I'm not happy that Dialog didn't
switch it. I mean, I grew up with that as well,
and customers, you know, it's the same problem like we had with doing representation of a one element vector. You're going to make change that's going to make everybody's programs fail.
Right.
It's kind of a deal.
So let me hear. What's your reason? Why should up arrow be first and right shoe be mix?
Well, because and first are different functions, and first is kind of a fundamental function. You know, it's something that even Lisp had, first and rest. We never had a rest operator, although a rest function. But we did consider that for a long time, to have a rest function. We looked at Lisp long and hard, actually.
Oh.
I don't know if you remember, there was a paper in one of the conferences by Alan Perlis, who's a great mathematician. And the paper was called, "Should APL and Lisp be merged?" And the answer was no. Well, what a great paper that was.
Well, I mean, some will claim that if you merge APL and Lisp, you get K.
Well, K does some pretty amazing things, I think, actually.
Yeah. So what would the symbol have been for last?
For what?
Which glyph, which symbol would have been used for the last function?
Well, we were looking at matic down arrow.
Ah, I see.
So we'd have, and on vectors, it made sense. But when you looked at higher rank arrays, there really wasn't any reasonable definition that we decided was worth doing. Another thing we spent a lot of time on in the early days, which never got done, was adding the concept of multi-character scalars. I mean, clearly, if you say 234 with no spaces, that's a scalar 234. Just takes multiple positions to write it. We wanted to have what you might call symbols. You know, the ABC ought to be a scalar. And a lot of the uses of nested arrays are done only because ABC is not a scalar, it's a 3-element vector. And so you nest it, make it look like a scalar.
And classic mistakes from this. A vector of character vectors on
Yeah.
the left of iota and a single character vector on the right of iota. Why is it giving me a strange result? Right?
That's right. Absolutely. Yeah, it's a source of a lot of errors. And we even came up, we were going to use a leading underscore as the syntactical trigger that what followed was going to be a symbol. So you had an underscore ABC, that would be the symbol ABC. And it would be a simple scalar.
But wasn't the underscore a valid identifier character?
I don't think it is a valid character, is it?
Well, it certainly became eventually.
Yes, it did eventually. But can it be the leading character? I remember,
no, it cannot. I just tried it in APL2 and it certainly cannot. You're right.
and so we could tell, what was going on. We couldn't convince ourselves, let alone our management, that the effort to do this was going to make a big difference to our users.
Wow, so that's I didn't realize there was difference in the naming allowed names in the APL2 versus say dialog APL. Dialog allows leading underscores and names, and so that's why it was reserved for that extension that never happened.
Yeah, I think so. Yeah,
Because it's allowed internally in names, just not leading.
that's right.
Wow.
Just like a number internally, but not leading.
Yes, yeah. Oh, so it's considered
Well,
like a digit, yeah.
Yeah.
Oh,
So,
that's fascinating. Wow.
and,
Such a tidbit.
go back to the history and find out all these things that we didn't do. And
I can tell you the dialog considered
an
adding
interesting
symbols.
paper.
Yeah. Oh, well, you have to write it. I can't write this. I don't know.
Of course, that information is pretty much lost. I mean, it's like the information when you make a bad decision, you'd like to know, well, what led you to that decision. If you made a right decision, what led you to them? We tend to not make a record of those decisions. We know what the decision was. We don't remember exactly why it was made.
Oh, wow.
The system labels was a big one because we had done that with a lot of things. For example, how did that work? We had
So what you had for
system label that determined this is the execution if this function is called monadically, and then you could have a separate definition if it was called dyadically, instead of checking for the name class,
which is ugly.
say, does it exist? You could use a system label to say, here's the definition for monadic.
Right.
Another one say, here's the definition of dyadic.
Yeah. Well, I have another question for you. Do you know about Lenora Mullen? That's mathematics of arrays. Ever heard about it?
What's the name?
There's a paper or something called Mathematics of Arrays by Lenora Mullen or Mullen. No, if you don't know about it, then I won't. I think she tried to like formalize the theory around multidimensional arrays as a removed from the concept of a programming language, but not. I was just wondering whether you're familiar with it, but if not, that's fine.
No, I'm not aware of that paper. I am aware of Lenora Mullen, though. I mean, I worked with her manager at Yorktown.
Yeah.
And I've lost track of her. I assume she's someplace in Canada now, I think I heard.
I think I can continue. We have this this podcast I'm in, the Arraycast, and I can give you the information for that if you're interested. And she wrote in an email to us about that. So whatever. Somebody suggested I should take it up with you. If you want to be in touch with her again, I think we can arrange that. So.
Yeah, I'd be curious to see where she is these days. And Mike Jenkins is somebody else I've sort of lost track of. He was at the university in Kingston, Ontario, I think. And I expect retired. Fine, but he was at Yorktown the years I was there and was responsible for the definition of domino, matrix inverse, and matrix divide,
Oh.
which we had to extend to complex arithmetic.
And overdetermined matrix.
Complex arithmetic? I don't think so.
Does what? What did you say?
Does dialogue have complex arithmetic?
Yes. Just like APL2 does, yeah.
I should know that.
No, I mean,
I've been working with dialogue a lot lately.
take the square root of a negative number and find out. It doesn't have the various input forms that the APL2 has. Like APL2 allows you to do like angular polar form input, and it converts it. Dialog
Yes.
doesn't do that.
Yeah, degrees or radians.
Right. But other than that, yeah, it works fine. And then an extended circle function as well. Lots and lots of extra things on the circle to handle various interesting things.
Yeah, the things I've been doing with dialogue really don't have much to do with the definition of the language and have more to do with the implementation of the language.
So we're almost at the hour. I have to ask you, let's say you reinvented APL today. What would you do differently?
Well, there's a tough one, but it's the kind of thing I think about some because one of the three jobs I currently have is with a company in Northern California that thinks they have a better way to build parallel computers. And if I could turn my screen around, you'd see there's one right in front of me, one of these experimental parallel machines. And the thing that makes it special is that attached memories sometimes belong to a master processor and sometimes they're assigned to sub-processors. So we have defined what we call a disjoint array. And a disjoint array is one, when all these memories are attached to the main system, then this is an array which is a local array. But with a hardware switch, parts of it become associated with these sub-processors, and now it becomes a distributed array. But without moving any data, just flipping a hardware switch. And that's
so
property behind this machine. It's called a DAC machine, which is disjoint array computer, DAC. And I've been putting a lot of thought what I would like to actually implement disjoint arrays.
But would it make a difference in the language itself, or would it just be the implementation that's different?
I don't know yet, but in fact we would have to make some changes in the language because it's there would be so much traffic going back and forth in these different arrangements of the memories. I fear I'll never actually get to do this at this point in my career, but it's things I dream about, sort of, what if I had complete freedom to do whatever I wanted?
But it's interesting, right? Because computation on say graphics, what's traditionally called graphics cards, but it's really dedicated array processors is what they are. There's a huge overhead of sending all the data to that external processor and getting it back, and often it doesn't pay off. So this solves that problem, that you don't have to transfer the data.
Yes, and ultimately I would want to go even further than that, so that all storage that is available to the machine is part of your random access memory automatically. I mean, how many, I've written a lot of programs where we take advantage of the memory mapping facilities and the various implementations of APL to get a really efficient way to handle external data. I'd like to make that the standard way to handle. I would like something like an external disk drive to look like main memory, and the things in there are arrays. And when you plug this in, suddenly you have all these arrays that are available to you.
So you should be able to reverse the order of a file directly without loading it into working memory.
That's right. That's right. And we're at the point now where with I don't want to get too much into hardware. I don't care much about hardware except that I wanted to do what I wanted to do. But the USB, we use USB connections on this DAC machine. And USB 4 is getting to the point where it's almost competitive with your RAM on a machine. So why not treat it as RAM? You'd have to change the operating system so that the address space was no longer contiguous, but with paging tables, that's doesn't require any change to the hardware to do it, just some programming to make it all work. And in the DAC machine model, then you would just have this huge main memory. And when you flip the hardware switch, suddenly some parts of those memories would appear in the subprocessor's memory instead of the main computer. Again, without any sending of data, and just the flick of a switch is instantaneous. Little bit of overhead on the operating systems to recognize what happened. But that little bit is independent of the size of the data.
So, but I suppose that requires that. Sorry?
I don't think I'll ever get the chance to actually do that at this point.
Well, okay, but the idea is still intriguing, and I guess APL is in the perfect language for that because it addresses whole arrays like this.
Absolutely. What else? What notation would you use to describe these arrays? And of course, we've gone far enough where we even find what if you plug in one of your old USB drives? Well, that'll look like a vector of files. It would still look like everything would still look like an array to the machine, but for legacy purposes, it would actually be implemented as whatever file structure, NVMe or NTFS, whatever was actually, on that drive. We'd make all that. Maybe if things, we're now making presentations to customers of this DAC machine and describing arrays to them. And a lot of customers really don't know what arrays are. And I've had that experience over and over again. We did a big project for the US Department of Defense that succeeded where other things failed, basically because APL had Boolean arrays. And we could do Boolean logic to do things that they were doing, these huge relation joins and things like that. And it's a concept they just never heard of before. And we've had a lot of good business with them over the years.
Had the advantage that the state you were dealing with all fit into memory.
Yes, yes. And most languages don't have bits. C++, the best you can do is a byte for logical values unless you write a lot of code around it. Well, that code is what APL already has written around it. We have a bit as one of the internal storage types in APL implementations, and they don't in Ada or Prolog or C++. So they were quite astounded at what we were able to do.
Sounds
There are a
like
number of other things that people have been doing, trying to move the processing into memory. It's a little bit artificial, but it turns out most machines nowadays spend much more energy moving data around than they actually do processing it.
Yes, yes, that's right. In fact, I've seen reports of the amount of the computer resources that go into actual computing, as low as 10% or something like that.
Yeah.
And that's what we're doing with the DAC machine. We can move terabytes of data in an instant, what appears to be an instant.
Does this DAC machine have multiple physical processors, or
Yes.
they sort of integrated with the memory? How does that work?
There's one master computer. We can't use the word master anymore, so we call it manager. And then
Okay.
there's a series of nodes. Here's one of them. This particular one is 64-bit ARM device with a couple terabytes of memory. And the machine I have, you can put 8 of these in. Up at the office in Northern California, they have one that you can put 24 in. We talked about 128 node machines. And so you can distribute data from the manager to these nodes by flipping the switch if you've loaded up the memory correctly to begin with, with this in mind of what you're going to do with it. And then
Can
you
the switch be triggered programmatically, or is it a physical switch always?
Say again?
Is the switch programmatic? Can the switch be triggered programmatically, or is it always a physical switch?
It's a physical switch which is changed programmatically. I mean.
Oh, so it's actually both.
And there is code that will tell the switch which state it should be in.
But there must be some restrictions then that when each sub processor then is or node is done processing its chunk of data, the data must maintain the same length, right? Otherwise you get non-contiguous results in memory once the switch is flipped and the data comes back again to the main process.
It looks more like a nested array.
Okay.
The manager, it looks like, has a vector of arrays. And those arrays that get, when you flip the switch, there's one switch between the manager and each node.
Okay.
You flip, now the node has that array.
So the programmer
in the manager.
So the programmer will say, okay, this amount, this data, or declare this giant array to be in these chunks, and then they are located in memory in a place where it's possible to switch them, right?
That's right.
Okay.
That's right. And there's a network connection between what we call the nodes and the manager for sending commands back and forth. We can tell when the node is finished doing its computation and when it's okay to bring that result back. And that'll happen at different times on different nodes. And
sounds like one of the advantages is that when a node owns a particular piece of data, there's no contention. Because normally if you have shared memory, you always have to worry about if another process is trying to get at that memory at the same time, it interferes with performance like crazy.
That's the big problem with traditional parallel computers, is the path to memory and the memory contention. And with these nodes, that contention is 0. It's not small, it's 0.
This way to share memory is not to share memory.
Sorry? I missed the last comment there.
Oh, the best way to share memory is not to share memory.
Yeah, really. I mean, you can buy a machine with hundreds of processors on them, and especially when you get into, FPAs and these processors, like the old Math coprocessor on the 8086. They're kind of like that, but you got to get the data into them. And this is a much simpler architecture with just this switch. Now you have all of these simple general purpose computers. You can do whatever you want with them. And each one can do their piece of the work, and there's 0 contention.
And they can cooperate by just exchanging chunks of memory that they can see.
Yes, but each nodes cannot communicate among themselves. They can only communicate to the manager. Everything goes through the manager. the thing that started out this program was an APL machine that was written by, not written, but built by somebody named Sauermann in Germany. And they built hardware to do APL type operations. And that was sort of the starting point for this project.
There have been quite a few different APL machines that have been built.
Oh, yeah.
I spent some time building one based on an array processor.
Yes.
And all kinds of people, starting with, say, CDC Star Machine, had a version of APL hardware that was specific to it, although it wasn't good for general APL.
Yeah,
I remember Bob Wernicke and a number of things. They've done a number of things to make matrix algebra work on the Star Machine.
But yeah, with general APL things, that's a much more difficult thing. And we can build these things. They'll do wonderful if you've got really big arrays of floating point numbers. We can do wonderful things. But you go look at an insurance application or something, you find the average length of a vector is like 12, 1 per month. And so to be practical, you got to be able to handle non-huge data if you're going to handle a general purpose case.
There are a lot of cases like this. There was an early Intel processor, which they thought was going to take over the world because it could do any sort of list processing in a single instruction. But it turned out 2 + 2 took just as long as a very complicated list instruction.
That's right. That's right. I think things like this kind of hardware is eventually going to come about. And I think APL or an APL-like notation is the way to control them. I was quite excited. We were dealing with Hewlett-Packard for a while, and they had a project which they called The Machine. And they even put ads on the television for The Machine, which basically was a flat address space where all storage looked like it was in memory. Well, they gave up on that. And
that was something we actually did with the APL machine in the early 80s. And it had a disk attached to it, but it wasn't addressable as a disk. It was just memory. And essentially, we had a virtual memory which was persistent. The idea was that it just contained APL objects. And to pull the power, it just did a checkpoint at that point. And when you plugged it back in, it came up in the state it was in when you stopped it. And the only I/O we had was for magnetic tape, basically getting things from the external world into the machine or out.
Nothing new under the sun. I think that kind of design is probably going to end up revolutionizing the computer world again. I mean, the technology has reached the point where this kind of thing can be done on general purpose computers. And the kind of thing that Hewlett-Packard had hoped to do, and that I think hardware is going to move in that direction, and APL is going to be the way to manage them.
Well, it'll move that way. It's not clear whether APL will be the language that gets most popular, but it's one that's a good candidate.
It's the one I would choose, as I can say.
I think most of us would agree with that.
Yeah. Getting that out into the real world, that's hard. But, a lot of products that have been around in the last decades owe their existence to APL. Mathematica had for many years, one of their first references was to APL and its influence on how they handle arrays. More recently, they've taken that citation out of their product, which is interesting. The first spreadsheets, certainly in APL. I remember doing execute each.
Oh, yeah.
So we have a poor spreadsheet.
There were a lot of funny issues in the early days of APL because when I was with Burr, I was there around 1974, and we were in regular contact with the Philadelphia Science Center. And so Jim Ryan would have Aidan and Ken over to have a look at what we were doing. and at quad A, and Aidan said, "What's that?" "Oh, it's just the alphabet." And we concluded later on, the reason IBM had quad AV is they thought we had.
Yeah, I had many pleasant visits to Jim Murray down there. And I remember the one where he's running this program in a loop, and he told called up the operator and says, "Reboot the machine." And they rebooted the machine.
Yep.
And when it came up, the computation continued from where it left off.
Yeah.
As long as you're not doing file things, you can actually do that. They had a lot of good things, and they had system variables before IBM did. I think they used Delta before. And
True.
I remember
there were a lot of funny issues
quad,
there.
we were all
There was
in
one
quad.
point where Jim was showing a lot of his things that he was doing in our version of APL. And Aidan, a little huffily, said, "Well, what are you going to call your language?"
Yeah, yeah.
And Jim said, "Well,
Too.
considering that the ever-expanding universe, we've been thinking about calling it Nebula, until we found out Nebula is the cloud and the urine specimen."
Great.
But there are a lot of cases where various misunderstandings to language features.
Yeah. Oh, yeah. Yeah. Do you remember Sybil at Burroughs?
Oh, yeah. Sybil's your Burroughs implementation language.
Yes. A recursive definition.
Yep.
I have been keeping track of acronyms, and that's a recursive acronym that I include in that document, which I was going to give at an APL meeting in Germany, which has been canceled every 6 months for the last 2 years.
Yeah. There were a number of contentious issues between us and the Philadelphia Science Center on shared variables. I think the big argument was Aidan was absolutely adamant that they were a variable that was shared between two workspaces. No, it's not. It's a communications channel. We have these funny issues where if you had a shared variable and you tried to save your workspace, you was full because it tried at the last minute to take that shared variable and copy it into your workspace.
Yes. And
our attitude was, if you don't ask for it, you don't get it.
Yeah. I think IBM used shared variables for a lot of things that they were not appropriate for. Using shared variables for file systems really doesn't make sense. It ought to be synchronous. And like you say, shared variables, they might look synchronous, but they're really not.
It's a case of everything looking like a nail.
Yes, yes. Yeah.
Okay.
But even if you realize that they're not synchronous, they're still very valuable for getting things connected up. Later on, when I left Burroughs and I was using shared variables to communicate with other processes, it worked very well. You just had to understand the discipline of how you use it.
That's right, and that is something you did have to understand. It was not obvious from it. But you know, similar things are going on in other places now. In the C++ world, you can have dialogues where you say, okay, the information in this is this variable in my program. It's kind of the same thing, you know, under the covers, it's moving data around. I suppose they could get a worse fool if you had the wrong data in this dialogue. If there was but it's kind of the same thing that we had going in shared variables. I think I always quite liked shared variables. I liked being able to have the session manager on a computer different from where I was doing the computing, because it talks to the interpreter with shared variables. But like I said, I think we used them for things for which they were not appropriate. And
and there were a lot of rough edges in the original shared variables.
What did we call them? Files as variables, external variables. That was it. And that's a way that makes sense maybe to talk to files more than shared variables. except that, of course, the shared variable means it can be on another computer, which is an advantage.
Oh, yeah. One of the funny edges with the original APLSV was the implementation of system variables like quad IO as if they were shared variables. And this led to things like implicit error, which was kind of a mess until we turned that into somewhere it inherits its value.
I remember implicit, yes.
Oh, yeah, where you have an error and you have no idea what caused it.
Mhm, mhm.
Almost sounds like the issue we run into in dialog APL that has threads that can influence each other.
Oh,
A
yes.
thread sets a global variable and that affects another one. So it actually, at any given time, any expression that uses a user-defined name, you can't know what's going to happen when it runs because there might be a background thread that changes its value while your expression is executing.
Yeah, yeah.
Well, that was one of the realities working on Burroughs' machine and machines that had shared memory and multiple processors, that you could have a program that you didn't even know about cause your program to crash.
Yeah, that's not good. Okay, I mean,
want to go back and redesign things.
yeah, I think we have to round this off. We're a bit over time already, but Jim, thank you so much for being here. Really, really appreciate this. This has been a great episode.
Thank you very much for the invitation. I enjoyed this so much.
Well, you are always welcome back. I'm sure everybody here enjoyed this, and even though there are so many people here right now, but there are a lot of people view this afterwards, the recording of it. It's going to be published. Our next episode is November 21st, and I mean, I don't know who is going to be the guest at that point, but you're always welcome at these things. There are people who have been guests and then became regulars after that. Looking at you, Ron. So so that's perfectly acceptable. And yeah, well, sounds like there's even more that you could be speaking about. So maybe we'll do another episode one day.
Okay, if we ever get a real array machine going here, I'll give you a call.
Yeah, that would be amazing. So thank you so much. Thank you to everybody here, and it's been really great. Hope to see you around.
Great. Thank you.
Yeah.
Bye.
Bye-bye.